everything here. Let me get started. Uh-oh.
So, Mr. Cook, when do you release the questions that are going to be graded?
Oh, later today. So, yeah, I'll probably announce later today. And well, anyway, hopefully I say enough so I don't have to make another video. But we've missed so much class time this week that if I feel like I slight you guys some topic here, I'd rather go slower in class and just make sure we get through things coherently, as opposed to just rushing. So if I, miss something, I'll probably make a little video to just fill in the gap so that we have a complete, covering of the material in chapter 1. Because I do want to leave some time open Monday for like homework questions, right? So if I still have to cover material Monday, it's not great for this week. But that said, I will take homework questions today also if you got them. But let me begin here with a scripture. This is Psalm 111, verse 10. It says the following. It says, "The fear of the Lord is the beginning of wisdom. Good understanding have all those who do his commandments. His praise endures forever." So I always try to keep this in mind, that the reason we have the ability to think at all is because we have a good and gracious God. And we shouldn't take that for granted, I know myself, like, do I fear the Lord? Not as much as I should, right? I think we all, we're still sinning, right? So do we fear the Lord? Probably not as much as we should, right? But anyway, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask that you just help us today to glorify what we do, Lord. And in my prayer, Lord Jesus, amen. All right, so any homework questions in particular? Anything you guys are stuck on? So yeah. Number 7. Absolutely. So number 7, you've got x plus 2y to the 8th, and you're told that that's equal to, I kind of set it up, I say it's equal to x to the 8th plus ax to the 7th times y plus b xy to the 7th plus c, right? And then I say find values for a, b, and c. That's problem 7, right? So does anybody have an idea? How should we do this problem? Like, what's this problem intending to, like, check? Try to teach you guys a little bit more about what's the tool to use for this problem. Should you just multiply it out? Like, definitely not, right? Because, like, the 8th power is super annoying. But what you could do is use Pascal's triangle, right? So if we think about Pascal's triangle, we're going to be here a minute. Why did I make that 8? Dummy. Well, I mean, the thing is, you don't really have to do all this if you see the pattern too, So it's a fairly friendly question in the sense that it really only touches on the what? Thankfully, these coefficients are symmetric, right? So binomial theorem says that, if we look at, for example, I better not use a and b because we've got a and b have a different meaning here. But so let me use, say, alpha and beta to the 8th power. That would be equal to, like, alpha to the 8th plus 8 alpha to the 7th beta plus apparently 28 alpha to the 6th beta squared. Eventually we get to 8 alpha beta to the 7th plus beta to the 8th. So that's what binomial theorem would look like. And where did the 28 come from? Well, from here, right? But you don't actually need that, right? For this problem, because it only involves sort of the bookends, right? Like the leading term, and the next to leading term, the constant term, and the next to constant, like the one that's right before, like, you notice? So like, can you tell me what would the, let's see here. So what I'm trying to say is you can sort of think of this term, right, as being like that term, and you can think of this term as being like that, where alpha is equal to what? X, beta is equal to 2y, right? So you've got the 8 from the binomial theorem for both of them, right? That's part of it. But you've also got, like this term here is going to be 8 x to the 7th and then times 2y, right? This term here, on the other hand, is going to be like 8 times x times 2y to the 7th power, right? So that term will give you, what's 2 to the 7th? Well, it's 2 to the 7th times 2 to the 3. It's 2 to the 10th. That's a kilobyte, right? 10,024. So 1,024 xy to the 7th. 2 to the 10th happens to be 1,024. All right. So I think that A would be equal to 16. The B would be equal to 1,024. Let's see here, what would C be equal to? Oh, my bad. Oh, wait a minute. Oh, I'm a dummy. Oh. Rats. Well, there's two different ways of interpreting this problem. The one is that the term we're missing is somewhere in the plus dot dot dot. All right? In which case we should say C is equal to what? If C is a constant, if C doesn't depend on x and y, what must C be equal to? Is there any constant term in this? No, right? Because you've always either got an x or a y. Like it ranges from x to the 8th to like a y to the 8th. And then every term in between has a net power of 8. Right? Like this one's got 7 for x, 1 for y. My point is, because this is not a constant, like there is no constant term. So what I should have written there to make the problem more interesting, so you guys want to leave the problem as it is, or do you want me to fix it? Let's fix it. So we should have y to the 8th here to make it more interesting. That's what should be there. Which is why you're asking this question. Am I right? Okay. I'll have to judge this retroactively based on other questions you ask the rest of the semester. Then I'll go back and I'll decide whether or not you asked this question with understanding or just because you weren't sure how to start. Either is fine. But yeah, that's a typo. I should have a y to the 8th there to make this problem more natural. Okay? So let us add a y to the 8th there. Okay, so then what? So then like it's beta, like the beta to the 8th, which means that you've got like, so that's a 2y to the 8th, which is also known as 2 to the 8th times y to the 8th. What's 2 to the 8th? No. It's 2 to the 4th times 2 to the 4th, right? 16 times 16. 256. You could use a calculator. You know, you don't have to do that. 4 times 256 is 1024. So like, for example. Anyway, I took a bunch of courses in like digital logic design, so like I know powers of 2 a lot. I used to think about these a lot. But anyway, so I think with the modified problem, C would be 256. Other questions about the homework? Let me not belabor this more. The point of this was just to use the binomial theorem to try to see what the coefficients were. And again, it's kind of a pattern matching problem. Yeah. Do you guys want me to do one of the first 4 problems? Do you want me to see more of that? Because everybody did pretty bad on those. Well, not everybody, but a lot of you did. Probably wouldn't hurt to see another. So the key guys here is laws of exponents. Laws of exponents, for example, a to the s times a to the t is a to the s plus t, right? A to the s to the t power is a to the st. A to the s over a to the t is a to the s minus t. What else can I tell you? If we have a to the s, let's see here, times b to the s, that's ab to the s. This all assumes that a and b are positive, right? If a or b is negative, then there's some fine print that we have to deal with for roots and such. But a being positive, if we have the nth root of a, that's a to the what? 1 over n, right? What's a to the 0? 1, right? So these are the basic building blocks, if you will. Another rule of algebra that you should keep in mind is if you've got 1 over a over b, that's equal to b over a, right? So like a compound fraction, if you have a fraction, I sometimes will say the denominator of the denominator is actually the numerator of the fraction. So it flips like that. That's how we reduce a fraction. Okay, well with that set up, let's look at this. I'll look at problem 4. Let's see here. So we've got x squared over y to the minus 1 times y over x divided by 2 divided by the square root of x divided by y. Well, that's just a lot of divides by, isn't it? And we're supposed to set that equal to, c. I'll put it over here. C x to the a, y to the b. So the point is, use the laws of exponents to simplify this and identify what the c, the a, and the b are. Okay. So let me try to work on this a little bit here. So first of all, this first term I can rewrite as x squared times y. See why that is? 1 over, what is 1 over y to the minus 1? That's 1 over y, right? And 1 over y is just y. So this one flips up to just give me x squared times y. Now, whenever you have a over b, you can rewrite that as a times 1 over b. This is another algebra step which is super important to know about. Multiplication by the reciprocal is equivalent to division, right? This is true for symbolic expressions just as much as it is for numbers. So my life will be easier here if I instead look at this as y over x, right, times 1 over that, right? So 1 over 2 divided by the square root of x over y. So I'm just rewriting this. But what is division by a fraction? It's multiplication by the reciprocal, right? That's what this said. So applying that principle to this term right here, we have, and you're like, well, you could simplify that. I know I could. I'm just, hold off a second here. So this flips to 1/2 times the square root of y over x. Wait, hold on a second. It should still be x over y, my bad. My mind just hiccuped. So we're dividing by that, right? So that's, I'm just using this rule with b, basically b, let me circle. Now the way I'm doing it is not the only way, like this is just a way. So I'm thinking of this as being like this b, and it's going up to here, like this, right? But rather than dividing by 2, I'm multiplying by half, which is the same. Now, these two cancel, and that gives us x, y squared. I've still got the half. This gives me x to the 1/2 times y to the minus 1/2. Do I need to explain that further, or does that make sense to you guys? Like x over y square root is, I mean, sidebar here. Square root of x over y is square root of x over the square root of y, which is x to the 1/2 over y to the 1/2, which is x to the 1/2 y to the minus 1/2. If you're looking for an algorithm in what I'm doing, you're not going to find it. What I do is I apply these laws of algebra to what I'm facing until it looks simpler to me, and I just keep attacking it, because there's too many different problem types to have an algorithm for every problem type. You have to understand the laws of algebra and apply them with a goal in mind. The goal in mind being this simplification. Yeah? And my apologies to those who are not with us today because they're sick, because I have I forgot to move the camera. Sorry, guys. Well, you guys are here, right? So my apologies. All right, so let's clean this up. We're almost done for this problem. So what next? The half comes out front, right? And we've got x times x times, what is x? X is x to the 1, right? So we do x to the 1 plus 1/2, y to the 2 minus 1/2, right? So what do I got? I've got 1/2 x to the 3/2, y to the, that's funny, 3/2. So apparently a is equal to 3/2, b is equal to 3/2, and my constant out front, c, is 1/2. So if you got that problem wrong on the quiz, you should work all of these, right? And you should check with your neighbor and see if they get the same as you do. And if you disagree, maybe you should check with like Wolfram Alpha, something like that. Yeah? Any questions? All right, well, I'm going to go on and start talking about functions now, because I don't think you guys really have questions about the homework at the moment. And so let's move on here. I'm going to erase this business here. So can you guys, while I'm erasing, tell me what is a function? Anybody know? Can somebody define a function for me? What is a function of real variables? What's a real valued function of a real variable? What does it do? It takes an input and it gives an output, right? So that's a good answer. How many outputs? Just one, right? A single output. It has to be single valued. And every function has to come with a domain, right? The domain tells you the set of allowed inputs, right? And there's something called a codomain, which tells you where the outputs can go to. The places where they actually go is called the range. So let me just draw a picture. So I was draw some kind of funny. Here's A. All right, here's B. And you got a function. It goes from A to B. So this would be this function. This is a b-valued function of A. All right. So like the way this works is like we were just talking about, it has to be single valued. So we take a point here, x, it maps over to here, f of x, like so, all right? F of x has to be a single thing. And basically this rule, x maps to f of x for each x in A, and here f of x has to be an element of B, all right? Now this is a very general concept, right? Like A could be the set of barnyard animals, and B could be a list of world dictators since 1970. I don't know, whatever. Like A and B are sets. They could be all kinds of weird stuff. But for us, we keep it real in here. So we'll look at real valued functions of a real variable, which means for us, we're pretty much going to look at A as a subset of the real numbers, and we're going to look at B as a subset of the real numbers. So that's what a real valued function is of a real variable. Output's a real number, input's a real number, right? So you can, like you guys were telling me, you can think about it as a box, right? It's the machine, the F, so X goes in, and what comes out? Y equals to F of X, right? The output's Y, typically, right? Now, in this situation, the notation is this. F is a function from A to B, all right? Now, B is not the range, okay? So let's talk about this. The domain of F is equal to, you know, in this picture it's A, but it's basically X in the reals such that F of X is, you know, defined. That's kind of a schematic. That's our general rule. So either the domain can be stated by the problem, like we can just say the domain is such and so forth, or if we have a formula, we can try to figure out what's the domain on the basis of when that formula makes sense, right? That's our usual tact, is to use the greedy principle. Like the most X that you can get away with is got to be, that's the default domain. But the default domain can be replaced with something that's dictated by the problem. Now the range of F is equal to F of X, such that X is in the domain. All right. So if I think about the graph of F, what's the graph of F? It's the set of X comma Y such that X is in the domain and Y is equal to F of X. That's the graph. If you have a graph, that pretty much defines the function as well, right? Because if you can look at the graph, you can see which X values are allowed and which Y's they go to, which tells you the domain and the range, right? So just, you know, example, what if I tell you the graph of the function goes from this point -3 comma -2, sure, and it goes up here like that, beep boop, and this point is, let's say 1 comma 2, and then it comes up here at 2 comma 4, and then it just goes up and up and up, right? And there you go. That's a picture of Y equals F of X. What do the circles mean? What do the dots mean? The dot means that's where the value of the function actually is, right? So like that dot, that closed dot there, tells me, this right here, tells me that F of 2 is equal to 4, right? This open circle tells me that -3 is not an element of the domain of F. All right? So you guys tell me, what's the domain, given this graph, what's the domain? So it starts at -3, not included. And where does it stop? It doesn't stop at 2 though. You see, it jumps up here. 2 is defined right here. So there is an X value assigned to the graph. There's a point on the graph for each X value from -3 not included forever and ever, amen. So like the domain is -3 to infinity for this one, okay? And the range Have you guys ever heard of the codomain before? See, probably not. This idea is carefully excluded from pre-calculus books, but logically speaking, it's important because if you think about functions, you don't always know what their range is, but you'd like to define them. So having the codomain be the reals just expresses the totality of all possible outputs, whereas the range is the outputs which actually are achieved, actually are attained, all right? So we can always make the codomain to be the reals. That just admits, hey, we're looking at a real valued function. The range will be the subset of the reals which are actually gotten to by the graph, so like the actual y values. So for this one, the range, it's -2 not included, and it keeps going up to 2 not included. Then there's a jump, boop. So we do union with 4, which is included, my bad. And then it just keeps going up and up and up, so infinity. So that would be the range in this case. All right? If I ask this question on my college algebra final, I know I'm going to get 70% of the class getting this wrong. It doesn't matter if it was on a previous test. It doesn't matter if I've had 10 homework problems on it. For some reason, this kind of problem is really, really tricky to a large portion of the population. Now, you're in calculus, so you're probably not part of that population. But there it is. Did I ever turn my camera back here? All right, so let's look at some other examples of functions as a means of me introducing other functions to you guys, okay? So like, what are the functions that we care about in here? So first of all, like, you guys remember, if I give you a graph, how do you know if I give you a graph and it fails a certain test, then it's not a function. What's that test? The vertical line test, right? Is this a function? Yeah, it passes the vertical line test, right? Is there anything else you guys remember about functions that's interesting? How about we can build new functions from old? How do we do that? We can add functions, we can subtract them, we can multiply them, we can compose them, right? The composition of functions, we should talk about that. The notion of an inverse function, we should talk about that, all right? But let me first by just introducing some more examples. So let's see here. Example 2. How about f of x equals to, x plus 2 over x minus 3. This is an example of a rational function, right? This is a rational function. Why is that? Because its formula is a rational expression. What's the domain? X such that what? X is not equal to 3. So if we use interval notation, minus infinity to 3, union with 3 to infinity. Can you graph this? You should be able to graph this. Here's its graph. It's got a vertical asymptote at 3. B, 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 B. X equals to 3 is its vertical asymptote. The ratio of the leading coefficients is 1. It's got a horizontal asymptote of 1. B, 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 like so. All right. And it's got a 0. Where is it 0? Where does it cross the x-axis? What did you say? 2? Almost right. But we want a minus 2, right? So f of minus 2 is equal to minus 2 plus 2 over minus 2 minus 3, which is 0 over minus 5, which of course is 0. So that's where it crosses the axis here. The sign chart for this thing, which I could draw somewhere, perhaps down here is a good enough place. It's got 2 interesting features, minus 2 and 3. Those are the 2 places where the rational function is not defined or is 0. Those are the critical numbers. And if I plug in some points, I'll get it's positive over here, it's negative here, and it's positive back over here again. that sign chart paired with the fact that it does have y equals to 1 as its horizontal asymptote tells me that the graph looks something like about this. Let's see here. Yeah. So it goes to infinity that way, it goes to minus infinity here, and it's going to 1 asymptotically, both as you go to plus infinity and minus infinity in the x. All right? Graphing rational functions is something that you should already have in your toolbox, right? That's something you should have learned in pre-calculus. I'm just giving you a brief reminder. So the domain we could figure out just by looking at the formula, right? The domain of a rational function is we just have to do what? We have to exclude division by 0 as our enemy. What's the range for a rational function? That's a much nastier question because really you have to graph it in order to understand the answer to that, right? Or you could use a trick. I could show you a trick to do it. I'll show you a trick in just a second here. But anyway, the range, since we did the graph, what's the range? We got minus infinity all the way up to 1, union with 1 to infinity. The one value, y value, which is not included in any point in the graph is y equals to 1 itself, right? Everything else it's going to get covered. Let me show you a way to calculate the range without graphing. Maybe this is a trick you haven't seen. So let's look at this here. So I need to take a short detour. Definition, f composed with g of x is by definition f of g of x, right? That's the composition, right? Composition of two functions. We say g is equal to f inverse if what? If we have f composed with f inverse of y is equal to y, and f inverse composed with f of x is equal to x. This is for all y in the range of f, and this is for all x in the domain of f. That's an inverse function. Now, the only way the inverse function is defined is if the function is what's called one-to-one, right? It has to pass the horizontal line test in order to be an invertible function, right? And so the picture here is this. This is this is the domain of f. Over here is the range of f. F goes like this. F inverse goes like that. And they undo each other, right? But something to keep in mind is that there's a mirroring of domains and range for a function in the inverse, right? So like the domain of the function is the range of the inverse function. And the range of the function is the domain of the inverse function. See, that's kind of neat because what that means is if you can figure out the inverse function for a given function and you can figure out its domain, well, voila, you've calculated the range of your original function. And figuring out domains is easier than figuring out ranges. Because figuring out domains you can do by just looking for where the formula fails, basically, right? For a lot of examples. So let's put that into practice for my example 2. And in so doing, let me remind you guys how we find the formula for the inverse. So example 3. So let's find f inverse of y for f of x equals to x plus 2 over x minus 3. All right? So here's the algorithm I use. What I do is simply this. I put y equals to the formula for f of x, and now solve for x. How do you solve for x? Multiply by x minus 3. That's a good first start. A good first move. Good opening move. Now, some of you may have a misgiving about what I'm doing because you're like, wait, we're supposed to switch x and y now. I don't do that because I'm trying to find f inverse of y. So I'm not insisting the formula for the inverse function be written in terms of x. I'd prefer it to be written in terms of y, so I don't need to switch x and y. So solve for x. Now you said multiply by x minus 3. Great. Now we'll distribute. Yx minus 3y is equal to x plus 2. Put all your x's in one basket. So you got like yx minus x is equal to 3y plus 2. Factor the x out. X times y minus 1 is 3y plus 2. This gives me that x is equal to 3y plus 2 over y minus 1. Therefore, f inverse of y, in fact, is equal to 3y plus 2 over y minus 1. I feel like... Oh, that's fine, it's fine, it's fine. There you go. That's the formula for the inverse function. What's the domain of the inverse function? Yeah, y not equal to 1, right? The domain, in my current language, the domain of f inverse would be y such that y is not equal to 1, right? Which is exactly the range of the original function that we just saw in the graph back over there. I don't know, it's just a silly trick, but anyway, there it is. The larger point is, you know, what is an inverse function? It's a function that when we compose with the given function, we get back where we started, right? So, any questions about this? There's a couple of concepts I should talk about with you guys, which you probably haven't seen before, but they're really not that complicated, but they're new, probably for you, okay? So like, so definition, f of a is equal to f of x such that x is an a, and f inverse of b is equal to x in a, x in the domain of f rather, let's say, x in the domain of f such that f of x is an element of b. So here a and b are sets, so I'm explaining to you how we take a function of a set, or a function, or the inverse function, inverse image of a set, all right? The second concept is much more difficult than the first here. The first is pretty simple, right? So like if I give you just some illustrative examples here. If I have, for example, f of x equals to x squared, and I put a equals to the set 1, 2, 3, what's f of a? So I'm looking at f of, I'm looking at f of x, which is x squared in this case, right? X squared such that, x is an element of a, which is just a fancy way of saying 1 squared, comma 2 squared, comma 3 squared. It's the outputs of the function for the values in a. So, yeah. So this is literally just the set 1, 4, 9, right? How about this? What if I had f of, say, minus 1 to 4, not inclusive? What would that be? Same function. How would you figure that out? I take a graphical approach, see guys? So like x squared, we know what the graph of that looks like, right? What is it? It's a parabola. I feel like in a week without snow days, I would already had to talk with you guys about the vertex of the parabola and its connection to completing the square, but that time has come and gone, so we'll get back to it when we get back to it. But so here's the graph of the parabola, y equals x squared, and we're asking what are the outputs if the inputs are taken from minus 1 to 4 not inclusive, right? So if this is like minus 1, and over here is like 4, right? We're basically saying, what are the values that, let me make it purple so you can see it better. What are the y values that the graph takes on going from minus 1 inclusive, right, all the way over here to 4 not inclusive. So this endpoint here would be what? 4, 16, right? Because 4 squared is 16. The starting point here, it doesn't really matter, but it's minus 1, 1, right? So what values do we get x squared? We just need to think about the y, right? What's the answer? 0 to what? Yeah, 0. Is it included or not included? Is 0 included or not included? What do you think? What's that? Yes. Is that a guess or is that just a? Very good. Very good, because it is right here. F of 0 is 0 squared, which is 0. It is in fact there. Very good. So 0, 2. How about the 16? Is it included or not included? It's not included because that's an open circle up there, right? Because of the, I put the parenthesis here, which ends up not including that. So you guys can answer questions about the image of a function with respect to a given set by thinking about a graph and like where does it output. This is probably a new question for you guys, right? It's not something somebody told you about before, but it's a simple enough thing to talk about. The image of a function under a set is so defined. Now this here does not mean that the inverse image of f exists. For example, my function, example 4 right here, this is not an invertible function. Why? It's not 1 to 1, right? If you put a horizontal line through the graph, it has 2 points of intersection, right? It's not 1 to 1. So an inverse doesn't exist. And yet we can talk about the inverse image. For example, I'm going to get into trouble here, but what's like f inverse of, let's say, the set, 1 and 2? What would we be looking for here? We'd be looking for, x in the domain, x in the reals, such that what? Such that x squared is equal to 1, or x squared is equal to 2. That's what this would mean here. Sorry, that's supposed to go up here. My bad, I've worked myself into the corner. So what is that? Well, what's the solution to x squared equal to 1? Square root of 1 is one of the solutions, but also minus 1, right? Because if we have x squared equals to a, that gives us the solution x is equal to plus or minus the square root of a, supposing a is greater than or equal to 0. We can derive this with let's not derive it, let's just, that is a principle that we know. This is the square root property. All right, so here, the inverse image of 1, 2 is 4 numbers. It's actually 1, minus 1, square root of 2, and minus square root of 2. Those are the 4 points in this quote-unquote inverse image. If I wanted to graph this, let me graph what's going on. Like, here's how to think of it graphically. On the graph of the parabola, if we look at like 1, at this point and this point, if we look at 2, we get this point and that point. Those are the points which, like minus root 2 and root 2, and 1 and minus 1, these either square to 1 or they square to 2. Therefore, by definition, they're in the inverse image of 1, 2. So anyway, what I'm trying to say is for inverse image, you can look at the graph and kind of work backwards as well. All right, let me do another example, which is maybe less complicated. Oops, well. All right, well, yeah, fine. So if I have, let's say, this graph, f of x is equal to, let's say, 2x plus 1. And suppose I want to, see your example 5. suppose I want to find the inverse image of just the set from 0 to 1. What I'm looking for then is all of the points on the graph which go to 0 to 1. So like I can graph that kind of, the output being 0 to the output being 1. So this is 1, this is 0. It's this part right here. See, I know that the line crosses y value 1 at its y-intercept. So I just need to figure out what the x-intercept is. What's the x-intercept? That's where this is 0, right? So this is actually going to be minus 1/2, comma 0. See, if you input minus 1/2 to 0, the output is 0 to 1 for this function. This set maps to that set. If you don't get it yet, that's okay. Like, this is something you probably need to work a little bit on. And this is not the first thing on your list, by the way. First thing on your list is the stuff we started class with. You got to settle that stuff first. That's more important than this, all right? So what are the, let me just tell you where I'm going. I obviously need to make a video. So in the video, I will talk about the rest of section 1.4. In there, I will just talk to you guys about basically just the names of our common functions. So we talked a little bit about rational functions. I think you guys know what a polynomial function is, right? Function with polynomial. But there are other ones like we could have natural log of x or sine of x, or, and here's a new one, sinh of x, et cetera, et cetera. There's like a whole list of functions that maybe you have seen, maybe you haven't. And I'll talk to you guys about those in the video. It's mostly informational again, but I do want you to know about those because those are gonna be sort of the canvas on which we paint calculus. We're gonna use those are the characters in the play, if you will. We're gonna do things to those functions to study calculus, so we need to know what they are. But I don't expect that you've already seen everything in this chapter before. It's really, we're gonna learn the chapter as we go on, really, the truth be told.